Welcome to Exus the PodQuest. This is going to be an exciting day. We are going to be talking about a subject that I just love and have been wanting to talk about for quite a long time. It's the Big Bang Theory, the big theory of everything, how things got here, all of that stuff. And I'm super excited about it. We're going to have a fantastic guest on today. And I'm going to get to that in just a second. I'm going to set the program up here, get into our quote of the day, and then bring on the guest and get right into it and get all the details. Quote of the day. All right, here we go. I am fully warranted in announcing that the law which we call gravity exists on account of matters having been radiated at its origin atomically into a limited sphere of space from one individual, unconditional, irrelative, and absolute particle proper. That's by Edgar Allan Poe. That is from him in 1848, before Georges Lemaitre first introduced the subject and first developed the concept of the Big Bang Theory in 1927. So about 80 years approximately before that, here we have Edgar Allan Poe. And we're talking about how things got here. He came up with this. It was an amazing, amazing thing. So anyway, with that as a background, we are going to talk about the Big Bang Theory with our guest. Very privileged to have Dr. Inflaton Siegel with us today. And Ethan is a theoretical astrophysicist, science writer, and science communicator. He has a PhD in astrophysics from the University of Florida. He's taught many college-level courses, including currently, I believe, Lewis and Clark College out in Portland, Oregon. He is the author of two books, fantastic books. One is Beyond the Galaxy, and that was published in 2015. It's how humanity looked beyond our Milky Way and discovered the rest of the universe. And then also Treknology, the science of Star Trek from tricorders to warp drives in 2017. Very cool. Ethan has a science blog, very popular one. It's known as Starts With a Bang, and that's his website as well. Check him out at www.startswithabang.com. You got to go to that website and check out everything about Dr. Inflaton Siegel. He's written a legion of articles, all in these extremely popular publications, things like Physics Today, Scientific American, and Astronomy Magazine. But for me, mostly I know of Inflaton Siegel from the very popular column or series of articles in Forbes magazine, and that is known as Ask Ethan. All right? And I get the privilege today of asking Ethan on a much larger scale. Those are Forbes magazine. That's like people will write in and then he answers these questions in a discreet way, and it's a fantastic way. But I get the special privilege of asking him all these questions about today's topic, the Big Bang, the current state of it, and the newest challenges to it. Welcome to the show, Ethan. Dr. Siegel, love having you here.
Yeah, fine to call me Ethan. It's my pleasure to be here, and you get the extra privilege of having me in real time. So I don't have time to go do homework if I don't know the answer to anything you say. I just have to be stumped right here live. So let's see what you got for me.
All right, sounds great. Well, of all the great credentials, I would be remiss from saying, we went through all this stuff, but I'd totally be remiss if I didn't say that just as impressive is the fact that you definitely have to have the coolest facial hair in science. There's no question about that. Look at that with
Oh,
the handlebar mustache and the bisected beard. It's awesome. I just love it. So that's great. And I know you had entered
what's the
into.
point of looking so good if you're not afraid to show it off? You have to bring a little style into what you do. I cringe a little bit at how unstylish AI can be, and I'm so glad we still have people to be creative in ways that I believe computers never will be.
Absolutely, that's a great point, and the producer in the show is clapping his hands for that. That's an outstanding point. All right, let's get right into it. Let's talk about our topic, the Big Bang. Most people, I mean, almost everybody I know, certainly most people in the audience and lay people out here, when you ask them what is the Big Bang theory, they're like, well, okay, it's the theory of science and how the universe got here. But they'll say, look, everything was expanding and everything is expanding. So if you drive it all the way back, you'd keep going and going, you get to finally to a single point, I guess, the science calls a singularity, and that everything just popped into existence out of that, from basically nothing. And then expanded and expanded, and here we are. That's what most people think. But I believe you say that that's wrong, that that's not the current understanding in science of the Big Bang Theory. So let's have it. What is it?
All right. Well, I understand where you'd come from if that was what you thought, right? It was a big revolution back in the 1920s and 1930s when we started looking at these different galaxies that were out there. For a long time, people didn't even know that those spirals and those ellipticals in the sky were even galaxies beyond our own. It wasn't until we were able to get telescopes that were good enough that we can measure individual stars within them and say, oh, geez, I know what these stars are. We have them right here in our Milky Way. They've got to be super far away. So we actually measured the distances to these objects and determined, oh, yeah, they're not in the Milky Way at all. They're outside of it. So you can calculate the distance to these objects, to these galaxies, by measuring the light from the stars within them. And then you also have this other thing we know from being children and waiting for the ice cream truck that you can tell by listening whether that ice cream truck is stationary, whether it's moving towards you, or whether it's moving away from you, because the sound of whatever ice cream tune it plays, right? Pop Goes the Weasel or whatever. If it's too high pitched, you know it's moving towards you. If it's too low pitched, you know it's moving away from you. Well, guess what? Light is also a wave and it does the same thing sound waves do. If something's moving towards you, the light looks like it's higher frequency, which means for light that it's bluer. If it's moving away from you, it looks like it's longer frequency or redder. So we look at these galaxies and we measure how far away they are and we measure how fast they appear to be moving. And what do we find? That the farther away a galaxy is, the more its light is shifted towards the red, the more its wavelength gets stretched. So you say, okay, well, if I'm here and I see all these things around me in every direction, the farther away it is, the faster it's moving away. What could that be due to? And the way I like to think about it is the same way I would think about if I took a ball of dough with a bunch of raisins in it. Let's say I was going to bake some raisin bread, and I take a ball of dough with raisins in it, and now I imagine our galaxy is one of the raisins. What do we see as time goes on and the dough expands? Those raisins that are close to us are going to expand away from us, but only by a little bit. So the light from the nearby galaxy should only be a little bit redshifted. But the raisins that are farther away on the outskirts of the ball of dough, they're going to appear to expand away much faster because there's more dough expanding in between us and them. So they expand farther, faster. And for galaxies, the more distant they are, their light appears redshifted. So you put these pieces together and you say the universe is expanding. Great. So if I have a big universe today that's full of stuff and it's all expanding, then you're right. I go backward, backward,
Mm-hmm.
backward, backward in
Right.
time. And eventually I can say, okay, now we're far enough back that everything is at one single point. That's the start of things, birth of space and time. That's the Big Bang. Boom. And yeah, you're right. George Lemaitre first put this idea forth in 1927. He didn't call it the Big Bang, he called it a cosmic egg. George Gamow came along about 20 years later and built on this idea and expanded a bunch of consequences for it and said, I have a different name for it. I'm going to call it the primeval atom, very similar to something Edgar Allan Poe might have said, like you used
Yeah.
from your quote of the day. But what
Sounds
we
like it.
think now is, hang on, if I were to extrapolate all the way back to that singular moment in time, I would expect the universe to have a bunch of different properties. Number one, I would expect if we go all the way back to this early singular time, I would expect that we would have gotten up to arbitrarily hot temperatures. But when we look at this leftover glow from the Big Bang, what we call the cosmic microwave background, we can learn just from looking at this, we never got up to those arbitrarily high temperatures. In fact, the maximum temperature we could have gotten up to is thousands of times smaller than that maximum temperature. So no, it couldn't have been a singularity. And we also see a bunch of things we can't explain about the universe. Like if it got up to these super high temperatures and expanded everywhere at once from this singular state, then when we look out in this direction to the limit we can see, and we look out in the opposite direction to the limit we could see, we wouldn't expect those 2 points in opposite directions that have never had enough time since the Big Bang to exchange information, communicate, or achieve thermal equilibrium. Why would they have the exact same temperature? That's a weird thing. Why are there no leftover ultra high energy relics that all of our physics theories predict? Where are they? Why are they not in our universe? That's a weird thing. And why, if the Big Bang occurred and it's like the starting gun at that big race between cosmic expansion and the force of gravity trying to pull everything back together, why didn't gravity win and recollapse the universe? Or why didn't the expansion win and expand everything away from each other so that, things were on a runaway course? Neither of those things happened.
Hmm.
So all of these things, the fact that we didn't have an arbitrarily high temperature, that the universe has the same properties in regions that couldn't have talked to each other, that it's missing all of these high energy relics, and that you have this perfect balance between expansion and gravitation. Why was the universe born this way? Either, you can play the Lady Gaga route and say, oh, yeah, I'm born this way. Why not? Or you can say, hang on, I'm a physicist. When I see things that I can't explain, I don't say that's just the way God made it. I say, well, I want to look for a physical explanation for maybe how did it get to be this way? And when we looked for that explanation, we had this theory that was put forth a little over 40 years ago called cosmic inflation. And throughout the 80s, 90s, 2000s, and 2010s, we teased out the predictions from it. We improved our instruments and we made our measurements. And we found, you know what? This theory of cosmic inflation occurring before and setting up the Big Bang, this actually matches what we observe. The observations we made, the measurements we took, they support cosmic inflation and not this idea of a Big Bang singularity. So the Big Bang's still a great idea. It goes back to a very early point in time, but it doesn't take you all the way back to a singularity. It takes you back to a finite amount of time. And then before that, cosmic inflation was occurring. And we see its imprint written all over the face of the universe.
It's a very, very cool concept. But let me ask you this: when they first, when it was Alan Guth, right, who came up with initially came up with the idea of cosmic inflation, but didn't he have it coming right after the Big Bang at first, or is that just a misunderstanding? Seems like a lot of publications, a lot of science has it that you had the Big Bang, and then you had cosmic inflation almost immediately thereafter, and now it seems to be switched.
Well, so this is a big thing, right? Alan Guth did he is credited as the founder of inflation, and I think that that's proper. I think that he deserves that. But he wasn't the only person thinking about this, right? You had before Guth wrote his famous paper about cosmic inflation. You had Alexei Starobinsky writing, oh, if you had an early de Sitter phase in the universe before the hot Big Bang, then it could stretch the universe flat and provide us with a uniform set of temperatures everywhere. A physicist named Robert Brout, who's one of the physicists associated with the Higgs mechanism, published something very similar. There were a lot of people on this same track. In fact, one of them was a paper written by Rocky Kolb and his co-author, you might know as the founder of Mathematica, Stephen Wolfram, wrote just a month or two before Guth's paper was published, a paper about how you could have had this early exponentially expanding phase to your universe that set up and preceded the Big Bang. So it wasn't like
Hmm.
this was an original idea. But you have to realize for decades, from the 20s, 30s, 40s, 50s, 60s, 70s, when anyone said the Big Bang, those two things about having an early, hot, dense, rapidly expanding state full of matter and energy, and extrapolating all the way back to a singularity that marked the birth of space and time, people considered those two things synonyms, the same way like an
Right.
ancient Greek would have considered like raining, thundering, lightning clouds as being the same as Zeus. Like if you would have said like I don't believe in Zeus, that would have been the same as saying like I don't believe in thunder, lightning, clouds, and rain. Like they would have looked at you like you're an idiot. So yeah, that's what we thought is we said, oh, that's what the Big Bang is. It's both of these things. It's the early hot dense state and it's an initial singularity. And so when we came up with inflation, we said, okay, we've been calling both of these things, the early hot dense state and the initial singularity, the same thing. We've both been calling them the Big Bang. And now, if we have inflation, what we realize is okay, you had this early hot dense state, and before that, you had inflation. And then before that, oh crap, I don't know what to say anymore. There could have been an initial singularity. There could have been a birth to space and time, but that's not the only possibility anymore. Inflation is this weird thing where, in a very tiny fraction of a second, something like with every 10 to the minus 35 seconds that pass, whatever the scale of your universe was, it doubles in size in all three dimensions every 10 to the minus 35 seconds that pass.
Wow.
So in the next 10 to the minus 35 seconds, what you had doubles and doubles and doubles again. And then in the next one, it doubles and doubles and doubles again. And it keeps doing this. So by the time 10 to the minus 32 seconds have passed and you have more than 1,000 doublings that have happened, you realize, geez, that would have taken something that was smaller than the smallest subatomic distance that makes physical sense, what physicists call the Planck length. It would have stretched it to be larger than the size of the observable universe today. So, as wonderful as inflation did, it comes along with this new puzzle that, ooh, we want to know what happened before inflation. And the answer is we
Right.
can't, because by its very nature, inflation wipes out any information about the universe that existed within it prior to these final few tens or 20s or hundreds of doubling times of the universe. It's really only that
Interesting.
final bit of inflation that gets imprinted onto the universe we get to observe today. So some people still assume there's a singularity there. Other people debate whether there would be a singularity there or some non singular beginning that preceded inflation. Um, but nobody knows. So some people still say, yeah, Big Bang singularity, then something, then inflation, then the hot, dense, expanding Big Bang we know. Fine, you can call it whatever you want, but I want you to be honest and say hot, dense, expanding state going backwards, then cosmic inflation, and then we don't know. You have to be okay saying we don't know when the truth is we don't know.
Gotcha. And what's really, I'm very glad you're mentioning this because as I'm studying all of the stuff about inflation and the Big Bang theory, the question, the driving question that comes right at me is, well, what's being inflated? It sounds like you go back and there's something known as an inflaton field, which I'm not sure why anyone would name it that instead of inflation field, but nevertheless, I understand it is the inflaton field that gets it is the subject of the thing that's what's being expanded. It's being inflated. But I always want to know what came before the inflaton field, or is there something? Is there nothing? It was just always there. And so your points are really good. Is we don't know, right?
But that's also a really good thing you bring up. Like I work in this field and we talk about we say the inflaton field, right? Rolls off the tongue
Inflaton.
a little better, inflaton,
Yeah.
right? So we say we have the inflaton field. What does it do? Well, it's the field responsible for inflation. And then you say, well, how do we know anything about the properties of this field? And the answer is, well, we only know two things about it. One is that the field itself has to couple to the fabric of space. It has to be some sort of energy that is within space because it's the energy of space that can cause it to expand. So you have to hypothesize something. And since, as far as we know, everything in the universe is made up of quantum fields, we hypothesize this is also a quantum field. That
Okay.
doesn't seem like
And
too big a leap to me. There's some field, it has some energy, and that energy makes the universe expand in a very specific way that we say it makes the universe inflate. But then a second thing has to happen.
Mhm.
That inflation process has to come to an end. So, somewhere along the line, there has to be some sort of coupling between the inflaton field and at least one of the quanta that are part of the standard model, that are part of the known particles that we have today. So, at some point, all of this energy, this large amount of energy that was inherent to space, that we say inflaton field, but we know it was inherent to space and causing the universe to double, double, double in scale in a very short fraction of a second. At some point, that doubling stops. And this energy in space itself that we say in the field, but we mean was part of the fabric of space itself, it got converted into particles, antiparticles. Maybe it was quarks, maybe it was gluons, maybe it was electrons, maybe it was photons. It was something, though, some sort of known particle. This energy that was inherent to space got converted into particles or particles and antiparticles. And that transition cause things to rise up to a high temperature, not an infinite temperature, but a high temperature. And that's why I try to not say the Big Bang when I talk about after inflation, we have the Big Bang. I try to give that little extra caveat and say it was the hot Big Bang
Mhm.
because during inflation, there was a lot of energy, but it wasn't in this thermal energy that if you stuck yourself in it, you'd get hot. It was this field energy inherent to space that doesn't really couple to us in any way we know. But once you start converting that into quanta, into particles, antiparticles, radiation, whatever, now it reaches these very high temperatures, things get hot, and that is the hot, dense, rapidly expanding state that I call the hot Big Bang. So you
Okay.
have inflation, it occurs, it stretches the universe flat, it takes these regions that were once all together and stretches them across the universe so you can finally explain why different directions have different temperatures. It doesn't get up to those ultra high temperatures. They're high, they're hot, but they're not the highest you can imagine, which can explain both why there's no leftover high energy relics and also why we don't see that evidence of those ultra high temperatures imprinted in the afterglow in the leftover radiation from the hot Big Bang. And it does one more thing that I think is not generally appreciated. If you have space and it's expanding exponentially, getting larger, 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 you can't forget that on the tiniest scales of all, you have quantum fluctuations. So I have these little imperfections, these little fluctuations that happen on the smallest scales. What inflation's going to do, though, because it stretches things to larger, larger, larger scales, these little quantum fluctuations that would normally re-annihilate and disappear instead get stretched across the universe to larger and larger scales. So inflation also tells me, hey, when your universe is undergoes that hot big bang, when inflation ends and that field energy gets converted into particles and antiparticles and radiations, it's not going to be perfectly uniform everywhere. It's sort of like if you were to go and look at the ocean up close, right? From space, the ocean looks like it's perfectly smooth. But you get down to sea level and you look at it and you see there are all these little waves. And the waves might be small, they might only be a few centimeters high for an ocean that's kilometers deep. But those little fluctuations, those little imperfections still exist all across the ocean. And we think they existed way back when the hot Big Bang first occurred, because those fluctuations provided the seeds for all of the cosmic structure that would grow after them: planets, stars, galaxies, clusters of galaxies, and even larger scale structure. All of this had to be consistent with not only what we would predict, but then after we predicted it, what we would go out and observe. And it's only because our observations match those predictions so well that we're actually confident of this picture that, yes, we had inflation occurring. Then it came to an end, triggered and set up the hot Big Bang, and gave rise to the universe that has all of these properties that we see today.
Very, very cool. We're coming to the end of the first segment. We're going to pick it immediately back up with a second segment. But that was one of my questions: was how convinced is science right now that the Big Bang theory is the actual proper and correct theory of how everything got here? It sounds like you've touched on it and said that it's very we're very confident. Maybe a little bit more on that. Are we certain? I mean, where does it stand status wise in regard to that?
I mean, I would say it's unchallenged today in that there are some cornerstones to the Big Bang Theory, where if you want to rival the Big Bang Theory, your first hurdle is to at least explain the things we already know are true, that the existing Big Bang framework already explains. Like we talked about, why is there this leftover glow of radiation in all directions that's the same low temperature today? And
Hmm.
in the Big Bang, that is because, oh, well, everything was the same uniform temperature when inflation came to an end. And then the universe has expanded and cooled. So all of that radiation from 13.8 billion years ago, yeah, it was very hot 13.8 billion years ago. But as the universe has expanded, that hot radiation has gotten stretched to longer and longer wavelengths. So it's cold today. It's barely not even 3 degrees above absolute zero. But we see that radiation, and no other theory can predict that that would be there, right? There was a theory called the
All
steady
right.
state theory where they said, oh, yeah, that's just starlight that gets reflected off of dust clouds. No, it isn't. And we know that because starlight doesn't have a perfect black body spectrum. The sun is neither completely transparent nor completely opaque. And all
Right.
stars are like the sun in that regard, that there's not just one hot black body surface it all
Interesting.
radiates from. It's from a sum of black bodies at different temperatures. And that spectrum looks different than what we've measured this leftover glow from the Big Bang to be.
All right, we're going to have a quick break because of the turn right now, but then we'll pick it right back up with challenges like the steady state and other things, challenges to the Big Bang in just a second or so. All right, thank you. We are back with Exis the PodQuest. We're going to continue our conversation with Dr. Ethan Siegel, who is a astrophysicist, a theoretical astrophysicist of significant renown. We were talking about the Big Bang Theory, and then we're just getting into challenges to it, like things that other theories that might be out there. Before we do get into that, I do want to ask you one quick question, kind of going back to what we talked about in the Inflaton field. You had mentioned that goes, that becomes, looked at as the small speck. It's like smaller than the smallest elementary particle, if I've got that right. Or, first off, is that right?
Well, I mean, that's all it needed to start from, right? So you can
Right.
say, okay, I imagine all of this initial stuff in the universe. Maybe it started from a singularity, maybe it was huge, maybe it had all of these different regions with all these different properties. What inflation tells you is you just need one tiny, tiny region. It doesn't even matter how small it is, where inflation starts.
Right.
And once inflation starts in that one region, it takes over.
Okay.
Inflation is so fast and so relentless that even if you imagine an arbitrarily large universe beforehand, after the tiniest fraction of a second of inflation, inflation is now 99.9999999% the volume of the new universe. So
Gotcha.
inflation is great because all you have to do is start it somewhere, somehow, and that's going to dictate what the overwhelming majority of all of existence is going to look like and have the properties of.
All right, and if it was started at, by something that is as small, or it started as something as small as an elementary particle, a subatomic particle, could that have been that could inflation itself have been, what they refer to as quantum decoherence? Could it just simply have been the quantum entity itself having brought itself into existence and decohered, if you will, into what we have now as inflation, the Big Bang, and carrying forward?
Well, I wouldn't necessarily blame it on decoherence. I will say it possibly could have started as a quantum fluctuation. There is a type of empty state, a vacuum energy state known as a Bunch-Davies vacuum. And Paul Davies of the Davies, I don't remember who Bunch is, but he was one of the people who showed, if you have a quantum fluctuation in this volume, it could start off an inflationary event. Decoherence is normally what we talk about when you have quantum particles interacting with each other or interacting with the environment, and then you stop getting that quantum wave like behavior out, and things just start acting like classical particles, right? Things just start acting like things that smack into each other and bounce off, rather than things that do this weird interference with each other or with themselves. So I wouldn't blame it on quantum decoherence, but I could say it's plausible that inflation began from some vacuum state, some state of space-time that had a quantum fluctuation, and that fluctuation triggered inflation.
Very interesting. Okay, awesome. All right, let's get into some of the contrary, not contrary, but the alternatives to the Big Bang theory. You mentioned one, which is the steady state theory, and I believe that Fred Hoyle was one of the big champions of that state, as well as the quasi steady state theory. Give us a little bit more. What was that saying? What was the steady state about?
Okay, well, so you have to recognize that when the Big Bang was first proposed, they said, here are the four cornerstones of what we expect the Big Bang to do. Number one, because we started from a hot, dense state and it expanded rapidly, we expect we'd live in an expanding universe. And that was an observation that motivated it. So, of course, it's got to explain the expanding universe. Steady state theory said, okay, look, you look out and you see this universe that is perfect in space, where if you look at the universe on the largest scales, like if you were to take a box billions of light years on a side and like a big ladle scoop out billions of light years worth of volume of universe, cubic light years of universe anywhere, you're going to get roughly the same amount of stuff. It's only going to differ by like 1/100% or less, because the universe is uniform. It's isotropic. It's the same in all directions. It's homogeneous. It's the same everywhere. And the steady state theory said, and I'm going to do you one better, and I'm going to propose what we call the perfect cosmological principle. And I'm going to assume that the universe is not only the same everywhere, it's the same every when. That no matter when you look at the universe, it's going to be the same. You'll see stars, galaxies, etc., everywhere, even as the universe expands. And then, people were like, hang on, if the universe is expanding and there's the same amount of stuff in it, and you just increase the volume, then the density is going to go down, and it's not going to be the same over time. And the steady state people said, I got you. What's going to happen is, as the universe expands, we're going to create new matter within that universe. So as space expands, the density stays constant. So they proposed a matter creation field, and they said, look, it's not like you need to create a lot of matter. You just have to create like one hydrogen atom per cubic meter every 10 billion years or so. That's not that much matter. We can create that. And that's how the universe is in a steady state. And the Big Bang people said, all right, look, if our theory is correct, then what's going to happen is, when the universe was hot and dense, at some point it was too hot to form neutral atoms. And so when that point passes, when the universe expands and cools through that point, Then you form neutral atoms, and all of that radiation that was around is going to get released. And so you should see this leftover glow from the Big Bang that today we call the cosmic microwave background, but back in the day they had a much cooler name for it. They called it the primeval fireball. That there should be a primeval fireball left over from the Big Bang. They also said you can go back even further and imagine that it was too hot to form atomic nuclei. That if you had this hot Big Bang, the universe had a bunch of protons and neutrons in it. And early on, when it was hot and dense enough to form atomic nuclei, you would have started forming heavier elements, things like deuterium or helium or lithium, or even heavier elements. And so you should get this early phase of nucleosynthesis that tells you the universe shouldn't have been born with just hydrogen. There should have been some heavy elements there too. And the steady state people said, nah, that's not how you make elements. You make elements in stars. You start with hydrogen, stars fuse in the core. We didn't know very much about nuclear physics at the time. And they said, and that's where you make all the elements. And the Big Bang said, well, also, you start with, an almost perfectly uniform universe that expands and cools, and the overdense regions are going to gravitate. They're going to pull the matter in from their surroundings, and they're going to grow. And that's how you're going to get stars and galaxies and clusters of galaxies and all of this stuff. And so you expect to get structure formation out of it. So expanding universe, structure formation, light element abundances, and the leftover glow from the Big Bang, the cosmic microwave background. These are the four predictions of the Big Bang. Now, what was interesting is in the 50s, the steady state people had a big victory because Fred Hoyle, who you mentioned earlier, was one of four people who figured out how the elements in the universe are made through nucleosynthesis inside of stars. And he figured that out, and he was able to explain carbon and oxygen and all of the heavier elements from the periodic table using that. And he was like, see, you Big Bang people, you think the elements were made in the Big Bang, and they weren't. They were made in stars. So pack up your toys and go home. You're wrong about everything, including the origin of the universe. And the Big Bang people said, well, hang on. You only established that the heavy elements were made there. What about the light ones? They were still made in the Big Bang. And that's true, but we didn't figure that out till like the 80s. But that key evidence came in the 60s, came in the 1960s, where two scientists, Arno Penzias and Bob Wilson, were working in Homedale, New Jersey at Bell Labs with this new antenna they got called the Horn antenna. And they pointed it up at the sky for the first time, and they couldn't get rid of their noise. There was like, geez, no matter where we point it, we see this noise. It doesn't matter if it's day or night. It doesn't matter if we point it anywhere in the sky. We see the same amount of noise. And they were like, oh, crap, maybe there's something contaminating it. So they went and said, what's going on out here? And they inspected the antenna, and they found there were pigeons nesting in it. And they were like, that's it. We got to get these pigeons out of here. So they're out there with the mops and the buckets, and they're cleaning all the pigeon stuff out of there, cleaning bird shit out of the antenna. Like, it's a real, like, not what you think of as Nobel winning research, right? But on the other hand, they did all this cleaning, they did all this calibration, and they found that the antenna was still seeing something everywhere. The only time the antenna didn't see anything is if you pointed it at the ground. If you pointed the antenna at the ground, you didn't see it, but anywhere in the sky, you saw it. And they didn't know what it was. But 30 miles away from Homedale, New Jersey, is Princeton University. And that's where Bob Dickey's group was. And in Bob Dickey's group were people like David Wilkinson and Groth and Jim Peebles. And Jim Peebles just won the Nobel Prize a few years ago for his contributions to physical cosmology. But he had written a paper predicting all of these properties of the primeval fireball. And Bob Dickey was building what was called a Dickey radiometer that he wanted to fly on a mission to go up high into Earth's atmosphere, or maybe even above the atmosphere, to try and look for this leftover glow from the Big Bang. And finally, they got the call from Homedale, New Jersey, and Dickey's voice rang out through the halls at Princeton, boys, we've been scooped. Long
Hmm.
story short, Penzias and Wilson detected that leftover glow from the Big Bang. And over the subsequent years, they went and measured its spectrum and found it was perfectly consistent with what the Big Bang predicted and inconsistent with all other explanations. It was inconsistent with tired light. It was inconsistent with reflected starlight. It was inconsistent with anything else you can imagine. It is still today the most perfect black body ever measured in the lab or in the universe anywhere. So that was really when the sea change happened and people accepted the Big Bang.
Big Bang.
And by the way, what you described in the first half of the program about, well, it's expanding. And so back, boom, and then bang, that was the picture that took hold in the 60s. I remember when I was a kid in the early 80s, I had a poster talking about the birth of the universe, but it was old and it talked about the steady state theory. And I didn't learn that was wrong until much later in life. But I grew up understanding that the Big Bang was relatively new, right? For someone, I was born in 1978, for something that was only discovered in the mid 60s to prove the Big Bang, it was relatively new that we understood that as the origin of the universe. And then just 15 years later, this theory of cosmic inflation gets proposed. And it isn't until the 90s and 2000s and 2010s that we got the corroborating evidence in favor of inflation. I think it's easy to understand why so many people are still out of date in terms of their understanding.
Gotcha. Well, if the steady state is out and that's no longer really a relevant theory, what about the concepts of like a cyclical universe? That there's, yeah, the Big Bang happened and maybe inflation started right, at the beginning and then there's a Big Bang, but then also that it expands and then contracts over time and then expands again so that you're having continuous series or cycles of big bangs. It's something no, what they call the ekpyrotic universe or the big bounce theory, or just the cyclical universe theory. What's the thinking on that currently?
I mean, so as physicists, one of our jobs is whatever theory we have, whatever theory is the prevailing theory of the day, our goal is to try and knock it down, is to try and find where are the weak points here? What are the alternatives? What else could it possibly be? We don't want to assume we've got it right. So we try and knock it down. And so, one of the founders of inflation, early days, Paul Steinhardt was an early contributor to the theory of inflation. By the late 80s, he was disillusioned with it and said, like, you can get almost anything out of this that you want with the right inflaton potential. All you have to do is design one of these potentials the way you want it to be, and you can get almost any universe out. So I don't like this. So he tried, and he's still trying to come up with alternatives. And one of them was, like you said, this ekpyrotic universe theory that says, well, maybe instead of having an inflationary field, you had like two higher dimensional universes that collided and stayed this tiny distance apart. And that could give you something that looked like our universe looks today. And okay, but if you want to make a new theory, what you have to do is tease out predictions of if this is what the prevailing theory predicts, what does my theory predict that's different? That leads to something different that I can go out and observe and measure and see, is it the way the old theory says it is, or is it the way the new theory says it is? And so far, alternatives like the ekpyrotic universe, the big bounce universe, Roger Penrose has one called the conformal cyclic cosmology that's out there. Um, Either there's no difference between what they predict to what the inflationary Big Bang predicts. And so it's like arguing over how many angels stand on the head of a pin, or they do differ and inflation is right. And that rules out a whole bunch of classes of these alternative models. And that's kind of where we are today. We know from observations, things are very consistent with this early inflationary epoch where space expanded exponentially, got stretched flat, and seeded the universe with these quantum fluctuations. And then we see everything that arose in the aftermath. We see those fluctuations imprinted in the cosmic microwave background. We see the results of those growing fluctuations imprinted in the large scale structure of the universe and how galaxies correlate with each other. We see the leftover glow of the Big Bang, including those imperfections in it. We see the abundance of the light elements. We see structure formation. We've even detected something we didn't know was going to be in there and be detectable back when the Big Bang was first formulated, which is a background of relic neutrinos that were produced in the Big Bang. We see those also imprinted in the large scale structure and imprinted in the cosmic microwave background. A lot of these theories, like the conformal cyclic cosmology, make different predictions. They predict that there should be what they call Hawking points in the cosmic microwave background, and there should be like 20,000 of them. And what we see is consistent with there being zero of them. So it's not looking good for that. Roger Penrose disagrees, but evidence don't lie. You got to follow it wherever it takes you. Uh, Ekpyrotic universe has many of the same problems that cosmological inflation has, but it has extra problems too. Like if you're hypothesizing extra dimensions, where are they? If you're hypothesizing these two extra dimensional universes stay this tiny distance apart, what's keeping them from moving in any direction? So you have to hypothesize extra things. So far, that's really all we see is there's evidence for this early exponential phase and for the Big Bang being set up with the properties it has. There may be alternatives to it, but those are the hurdles you have to overcome. You have to reproduce the successes of the current theory. You have to explain something that the current theory can't explain, and you have to make new predictions that you can go out and measure where the two theories differ side by side and you can test them. The reason inflation is accepted is because it's done all three of those things relative to the original idea of the hot Big Bang. The same way we accept Einstein's general relativity over Newton's gravity because it reproduced all the successes, explained things like the precession of Mercury's orbit that Newton's gravity couldn't explain, and then made new predictions about things like the bending of starlight and gravitational lensing and the Shapiro time delay that have all been confirmed by experiment. That's the big hurdle that alternatives to inflation have to clear, and so far, none of them have come close.
Very, very interesting. I've read an article recently that touches and actually mentions Paul Steinhardt, or maybe it was even co-authored by him, with Avi Loeb from Harvard,
Oh,
and
is that with
it was
Anna Ihas as well
actually
from
I think no,
Hungary?
yeah, I think that was a different
The
one.
three of
The
them
one I
wrote a
just
letter in Scientific American about 3 or 4 years ago.
Right, and then I did look at that one as well, and then I believe Sabine Hassenfelder wrote something in support of that, or at least some basic support. But what I'm talking about is Avi Loeb and Steinhardt wrote an article, or at least are attributed to the concept of what they refer to as the cosmic graviton background. Are you familiar with that concept?
Oh, yeah. I mean, we don't call it that. We call it a gravitational wave background because gravitons and gravitational waves, like gravitons are just the quantum version of gravitational waves. But we have, from inflation, we expect that just like we expect those density fluctuations to be seeded by inflation, we expect there to be a spectrum of background gravitational waves generated by inflation that are imprinted on our universe as well. The difficulty with inflation is inflation tells you perfectly what the spectrum of these gravitational waves should look like. What they don't tell you, because this is model dependent, is what the amplitude of that spectrum is. If the amplitude's large enough, we're going to see it. If the amplitude is not large enough, then it may be impossible to see. Um, Other alternative theories predict different spectra for these. So, in theory, if we can measure it, then we can know is this consistent with inflation or not. But if we can't measure it because it's below some threshold, that doesn't tell us inflation is wrong, which is what Loeb and Steinhardt have contended before. It just means it's one of the models of inflation that doesn't have the large amplitudes. So if they're saying you can tell whether inflation's true or not by whether this exists, no, you can't. You can only tell if it's true or not if you detect it and you measure its spectrum, and it tells you if the spectrum is consistent with inflation or not.
Yeah, it seemed to me that they were
Avi
arguing
Loeb,
in this.
Paul Steinhardt, and Sabine Hassenfelder say a lot of things, and so do I. But when I say them, you can have confidence that I'm not lying to you or myself. And I wouldn't say the same about the other three.
Oh, gotcha. Yeah, because they seem to be arguing in that paper that if there is a cosmic graviton background, as they labeled it, then that would eliminate the idea of inflation as an existing theory, because they said the Big Bang and inflation should not lead to this what they call the CGB, the cosmic graviton background. You're saying no, that's not the
Yeah,
case,
I
right?
mean, I wrote a paper on this in 2005 to show how the kind of cosmic gravitational background you get if you didn't have inflation and just had a singular hot Big Bang is the same gravitational wave background you'd expect if you did have inflation setting up a hot Big Bang, but you also had extra dimensions in your universe at some scale below the reheat temperature, but scale below the temperature of the hot Big Bang. Like this is old news. So
Okay.
I don't know what Loeb and Steinhardt are doing, but the answer is apparently not their homework.
Gotcha. All right, and we're kind of running out of time. Unfortunately, it goes so fast. We got about 5 minutes left. I really want to ask you about where things are in science on the matter and antimatter asymmetry. Where are we on
Ooh.
that program?
This is good. This is one of the big unsolved problems in physics.
Yeah.
Everything we've ever done in a collider experiment, in a particle physics experiment, has only either created matter or destroyed matter in equal amounts with creating antimatter or destroying antimatter. But our universe, including us in our universe and our solar system and the stars and the galaxies, not just our own, but all of them, they're made of matter and not antimatter. So why? Where did this matter over antimatter dominance come from? This is one of the exciting things that I think particle physicists are on the frontier of detecting. When particle physicists say, we want to build a new collider because we want to study the Higgs boson and the electroweak phase transition, that's one of the hugest, most accessible places where you could create more matter than antimatter if the physics is
Wow.
right. Now, it could have happened much earlier at much higher temperatures, right? There are many scenarios. There's gut baryogenesis, there's leptogenesis, there's Affleck-Dine baryogenesis, which happens in supersymmetry, but there's also electroweak baryogenesis. And the electroweak scale is something we can access at colliders. So when physicists tell you things like, I want to build a Higgs factory to create large numbers of Higgs bosons and see how they decay, or they say, I want to build a new collider at even higher energies and I want to collide relativistic ions at those ultra high energies to see if I can create baryon number violating interactions, they are talking about, I want to try and get to the bottom of the matter antimatter mystery. We have theoretical scenarios for how it can happen, but we don't know how it actually did happen. We're here, so there's evidence that it happened, but how is one of those big holy grail questions in physics and astrophysics that we're still trying to answer.
Wow, that's fantastic. When I looked at that question and I wanted to pose it to you, it dawned on me because I'm putting together another article that I saw recently about primordial black holes and whether or not there could be some tie-in between that. Maybe there's antimatter that's kind of trapped within primordial black holes, but I don't know. I mean, then I saw, no, I wanted to chat with you about it. Unfortunately, like I said, we're running out of time. Only a couple minutes left, so I'm going to have to wrap up. Maybe we can revisit this on another time. I drafted an 18-page outline. I got to page 2. So there we have. We got a lot more to talk about. But let me say to the audience, again, Dr. Ethan Siegel is the author of 2 great books, Beyond the Galaxy and How Humanity Looked Beyond Our Milky Way and Discovered the Entire Universe. Also, Treknology, the science of Star Trek from tricorders to warp drives. Author of a ton
Can
of
I give
different
you a
articles.
couple
I'm not
more?
going to Yeah, please do.
I wrote a children's book with my co-author, particle physicist Laura Manenti, called "The Littlest Girl Goes Inside an Atom,"
Oh my
and that
goodness.
might not be on my website, but it was published last year. And later this year, on October 8th, my first book with a little publisher called National Geographic is coming out, and it's called Infinite Cosmos, and it is the first National Geographic book about the James Webb Space Telescope and everything it's discovered.
That's going to be amazing. I really wanted to talk about the James Webb. We'll do that another time, but that's going to be great. Everybody should go right immediately or sooner to the website startswithabang.com for all the stuff about Dr. Ethan Siegel. It's fantastic thinking about the Big Bang Theory, inflation, all of that. Also, our website, which is accessthepodquest.com. We really want to thank you so much, Dr. Siegel, Ethan Siegel, for coming on the show, and we will be checking back with you and trying to get you back on the show for more. In the meantime, you go to his website, go to our website, like our YouTube. You go there, and we will be going ever forward.